I'm going to give a rare talk at our seminar. The seminar is devoted to knot theory, but we rarely consider knots. And here is a rare example. Oh, it's not that easy. Okay. It's not that easy. This is the famous pair. I hope I have drawn it correctly. The famous pair of mutant knots. And this one is called Conway knot. And this one is Kinoshita-Terasaki. Kinoshita-Terasaki knot. They are, I believe that mutant knots is something coming from horror movies. Some mutants terrorizing specialists in knot theory. And this terror is due to the fact that mutant knots are very similar to one another, and it is very difficult to distinguish between mutant knots. I must say from the very beginning is that we are unable to say that, for example, this knot is mutant. Being mutant is a property of a pair of knots, not of a separate knot. So this pair of knots constitute a pair of mutant knots. And what does that mean? Whether I do have colored chalk? Probably. Seems not. But there are two parts. No need, probably. There are two parts. One part, it's better to have a colored chalk. Probably Maxime will give me this one. I'll wait. There are two parts. The right-hand part is the same in both knots. Also, it's true for the left-hand part. Thanks. Let me. This part is the same. At least I tried to draw it as the same picture. The left-hand part also is the same, but they are attached to one another in a different way in the two knots. So it's indistinguishable, sorry. Here, probably that one. That one will work. That one will work. This is, in fact, the same picture, but rotated in the horizontal axis. If we take the horizontal axis and rotate this part, we obtain exactly the same picture.
Serge, when you say rotated, you mean reflected, right? Отраженное.
Нет, я имел в виду повернутое. Or probably it's a different direction.
Ну, ориентация поменена, да?
Ориентация
Или нет?
поменена, да, поменена.
Reflected, да?
No, probably it is rotated with respect to the vertical axis. Мы повернули вокруг вертикальной оси этот кусочек.
Понятно.
Now I can give the definition.
Сейчас, извиняюсь. А что с концами происходит? Я тогда что-то не очень понимаю.
Приклей. Ну, сейчас я дам определение тогда. The definition is like follows. Suppose we have a knot. In the 3-sphere. And suppose we have a two-dimensional sphere that cuts, that bounds a ball and that bounds a three-dimensional ball and intersects our knot at 4 points transversally. Then we may, so we have a sphere and 4 points at this sphere. This is a two-dimensional sphere with 4 points. And these 4 points are connected somehow by the knot inside this sphere. So we have some point 1, for example, and point 3, and some point 2, and point 4. We are unable to change, to rotate, or to reflect the picture inside the sphere so as to exchange the points 1, 2, 3, and 4 in such a way that the resulting curve will also be connected, will also be a knot. There are 3 ways.
Sorry, Sergei, can you repeat? We are able or we are unable?
We are able. У нас есть 3 способа переклеить этот внутренний диск к внешнему диску, когда наша двумерная сфера рассекает трехмерную сферу на 2 трехмерных шара.
Да, понятно.
И мы можем переклеить ее обратно, но поменяв местами точки 1, 2, 3, 4, так, чтобы узел остался узлом, так, чтобы это была одна компонента связности.
Да, понятно.
We do have 3 ways to reglue the 3-dimensional disk inside this sphere in such a way that the result will be also a knot, and any pair of knots obtained this way from one another is called a mutant pair. These are mutant knots. It is not easy to prove that these 2 knots are indeed different. It is a rather complicated task.
4 точки находятся на одном экваторе, там, на расстоянии π пополам.
Можно, пожалуйста.
И тогда, значит, я хочу считать, что эти точки, 4 точки находятся...
У тебя включен?
Я хочу считать, что эти 4 точки находятся на одном экваторе на расстоянии π пополам друг от друга, так что соединяются противоположные точки внутри узла. И тогда, значит...
Ну, это можно считать для одной половины только. Ну, там, ну да, внутри узла можно, а снаружи тогда то, что получится.
Да, то, что внутри. И этот внутренний шар я как раз... у нас один поворот, это внутренний шар симметрия относительно оси 1,3, второй относительно оси 2,4, а третья симметрия это относительно перпендикулярной оси. Центральная симметрия, да?
Ну, отражение.
Отражение.
Отражение, да. Well, so we are not going to preserve orientation of the knot. We also are able to orient.
Если отражение, тогда их гораздо больше получается. Ну вот, например, отражение относительно той плоскости, в которой лежат точки 1, 2, 3 и 4, относительно этого плоскости, в которой лежит этот экватор, там тоже что-то меняется.
Нет, мы должны поменять местами кусочки.
Нет, да, вопрос в том, что в каждом полупространстве узел сохраняется, а только присоединение меняешь.
Да.
Только приклеивание меняешь.
Только приклеивание.
Тогда, значит, все-таки нужно брать поворот, а не отражение, чтобы ориентация трехмерного шара сохранялась.
Ориентация, да.
Нет. Зачем?
Ориентация шара сохраняется, да. Ориентация узла нет.
Вот, значит, центральная симметрия относительно оси 1,3, оно сохраняет ориентацию дуги 1,3, но обращает ориентацию дуги 2,4.
Да, это да.
Вот, значит, нужно брать именно те самые осевые симметрии, которые сохраняют ориентацию.
Yes. Okay. And it happens that these two knots are different, and they have, in this case, one can prove that they have different, distinct genera. Genus. What is the genus of a knot? If you have a knot...
Сереж, извини, в принципе, если один узел задан, то у него, и ты фиксируешь гиперплоскость, по которой ты режешь, то из этих трех возможных парных узлов у тебя могут быть ты можешь получить три разных этих самых mutant pair, да?
Да.
Это такое бывает? Или...
Бывает. Сколько угодно.
Спасибо.
Не в этом случае, но бывает. То есть такая четверка узлов, любые два из которых являются мутантами друг друга относительно выделенной сферы.
Понятно.
Это сколько?
Это не то, что одна пара заменяется на одну другую. Это соотношение один ко многим.
Well, what is the genus of a knot? Each knot can be represented as a boundary, of a two-dimensional surface, dimensional oriented surface embedded in S3. Such a oriented or probably orientable. I don't know. If you have, for example, a trefoil, then we are able to construct such a surface it's like something like a form whose boundary is well, true. It's the Möbius band. And how one can construct an orientable surface.
Наверное, нужно нарисовать ее на торе, а нет, а на торе дальше. А он не будет выглядеть. На торе она отделяет только одну компоненту.
Okay, let me try to apply the algorithm for constructing such a surface. Like that. We have let me consider the knot to be oriented, and we can resolve each point of self-intersection of the diagram in such a way that so as to preserve orientation. So, for example, this double point must be we have orientation like that here, and the resolution preserving this orientation is like that. The same for this point, and the same for the second boundary. So what we obtain in this case two component oriented curve. Now we take a disk. For each of the two components. It's not the second disk. And then we glue the two disks together by bands corresponding to the double points, like that. And what we obtain a surface. It's easy to check that it is indeed orientable, and that the boundary of this surface is exactly our original knot. Let me forget about that. And the genus of a knot, the genus of K is the minimal genus of such a surface. Each time when we define a not invariant by a word like minimal or maximal or something like that, we obtain an invariant which is probably very powerful, but which we are unable to compute in any reasonable way. And for the genus, it is true as it is true for any other invariant of this kind. Nevertheless, one can compute the genus of the Conway knot, which is G equal to 3, and for the theta Terasaki knot, which is G equal to. As I have shown, it is easy to construct. It is easy to construct such a surface, but to prove that the genus of the surface we have constructed is indeed the minimal one is a complicated task. There are some general theorems. For example, the genus of a knot equals 0 if and only if K is the unknot. Sorry?
How do you glue the bands to the boundaries?
Each time we have such twisted, half-twisted band so as to obtain the original knot as the boundary.
Каждый диск выделяется ориентацией в плоскости, чтобы это было согласовано.
When we resolve all double points, we obtain a number of circles, a number of oriented circles. To each circle we glue a disk. We consider each circle as a disk, and then we glue different disks at each double point by such half-twisted band.
But the boundaries of the disks are not identified.
The boundaries are not identified. Не. Мы их потом склеиваем ленточками. А потом к каждой двойной точке доклеиваем ленточку, так, чтобы сохранялась ориентируемость поверхности. Well, and one would like to have some algebraic invariance. Distinguishing mutant knots. It happens, however, that most algebraic invariants, so to say classical algebraic invariants, fail in distinguishing mutant knots. And one can prove that neither Jones polynomial, let me start with Alexander polynomial, no Jones, no Collard-Jones, no Humphrey-Potter, can distinguish mutants. However, this is not true for colored Humphrey-Potet. Distinguishes.
You can distinguish.
Distinguishes between these two. This doesn't mean that it distinguishes any pair of mutant knots, but these two it distinguishes. Well, of course, the interest, the main subject of our seminar is Vasilyev's theory. Of finite type knot invariants. Knot invariants. And what is the relationship between mutant knots and what is the position of mutant knots in Vasilyev theory? First of all, there is a natural notion of mutation associated to code diagrams rather than knots. If you have a code diagram, suppose we have a code diagram, we have, I don't know, something like that. And we have what is called a share, about which Polina Filipova has told us several times. So it is a share. A share is a union of two arcs in our diagram, such that each chord, if a chord has an end on one of these arcs, then its other end also belongs to these arcs, and vice versa. A share is a pair of arcs in a chord diagram such that both ends of each chord either belong or not belong to these arcs. So if we have a share it's a pair of arcs, then the complement to the share also is a share. By obvious reasons, the complement also is a share. Because if an arc has, if a chord has an end belonging to the arc, to the complementary arc, так, чтобы она не зацепляла, like that, and here also. The complement to a share is also a share. And we can define a mutation of the chord diagram if we have a splitting of a chord diagram into two shares. This is complementary share.
Сереж, извини, а эти дуги могут пересекаться, или это объединение двух не пересекающихся дуг?
Ну, на самом деле нам не нужна ситуация, когда они пересекаются. Если они пересекаются, то у нас получается представление диаграммы в виде произведения двух хордовых диаграмм. И нам
то есть надо думать про две не пересекающиеся дуги, да?
Надо думать про две не пересекающиеся дуги. Мы можем, конечно, рассматривать пересекающиеся, но там ничего содержательного по отношению, по сравнению с мультипликативностью не возникает. Поэтому in this case it's suppose that these two arcs are not interlacing. Not
Intersecting.
Just interlacing. Lacing arcs. Well, and we can do a mutation of a chord diagram which consists in an obvious operation. We preserve one share, the complementary share. We cut off our original share and glue it back in one of the three possible ways. There are three possible ways to glue. For example, we can, let me draw it like that, and what we obtain will be like that. What is
sorry, can you repeat what's the operation? So you fix one share and then you glue the complement in what?
I fix one share.
Right.
I take off the other share and glue it back. Glue the two arcs back so that the four arcs together form the circle once again, but with some operation, either rotation in the vertical direction or rotation in the horizontal direction.
Can you replace top to the bottom?
Да, вот я это и сделал. На примере это и нарисовано.
A reflection rather than rotation.
It's a reflection,
Okay.
Ну, я не знаю, можно считать это результатом поворота в горизонтальной оси. Я и говорю, что это можно считать результатом поворота в горизонтальной оси. Можно.
В смысле, вот картинка, которая нарисована, вот эти хорды на этой картинке, это не хорды, а это теперь окружность, да?
Это окружность? Нет. Вот это окружность.
Вот на этой картинке можно нарисовать, там, если есть разные цвета, что к чему приклеено? Что было и чего стало?
Ну, что было тут нарисовано в другом месте? The green share is preserved, while the rose share is rotated along the horizontal.
Понятно, спасибо.
Well, what's important from our point of view is an obvious remark that mutation of a chord diagram does not affect its intersection graph. By obvious reasons. If two chords belong to one and the same share, then the intersection remains unchanged. Because inside the share, nothing happens with the intersection graph.
Нет, это я не понимаю, я извиняюсь. Вот можно сделать такую вещь? Вот взять, например, верхнюю дугу, начальную. Да, вот эту, да. И теперь приклеить ее так, чтобы она соединяла верхнюю точку левой дуги с нижней правой точкой. Ну вот как хорда на нижней картинке нарисована.
Это?
Да, вот эту с вот этой, да, так, чтобы это стало теперь частью дуги окружности, а вторую приклеить наоборот.
Нет, не понял. У нас дуги окружности остаются дугами окружности.
Ну, это приведет к тому, что правая дуга просто повернется отразится вверх и низ.
Один и 3 остались на месте, а дуга 2 и 4 поменялись местами.
Нет, но я могу... Сейчас, дуги должны приклеиваться только в дуге, а 3 и 1 должны сохранять ориентацию. Я не могу один отразить вертикально.
Нет, ты можешь зафиксировать любую долю. Я зафиксировал долю 1,3.
Когда ты говоришь «я фиксирую», это значит, что я фиксирую вместе с порядком, как они нарисованы. Да? То есть я не могу одну долю отразить относительно такой горизонтальной линии.
Нет, ну вот я долю 2,4 отразил относительно горизонтальной прямой, если хочешь.
Нет, ты верхнюю часть... ты верхнюю дугу приклеил вниз, а нижнюю вверх. А я говорю, нельзя ли эти дуги приклеить горизонтально, чтобы такие по диагонали, чтобы верхняя часть 3 приклеивалась к нижней части 1?
А тогда это... Нет, тогда у тебя будет 2 окружности, а не одна. Мне нужно сохранить одну...
Нет, одна.
Не понимаю.
Я верхнюю часть 3 приклеиваю к нижней части 1, и верхнюю часть 1 приклеиваю к нижней части 3.
Нет, они должны перемежаться. Ты не можешь 3 и 1 склеить между собой.
А я 3 и 1 не склеиваю. Я дугу вклеиваю.
Верхнюю часть 3.
Да.
Приклеить куда?
К нижней части 1.
Я говорю, что ты не можешь 3 и 1 склеить. Ты можешь...
Так нет, я дугу туда вклеиваю.
Ну, к дуге у тебя приклеиваются... К дуге 3 у тебя должны приклеиваться один конец дуги 2 и один конец дуги 4.
Ну, приклеить один конец дуги 2 к верхней части 3, а второй конец этой дуги 2 приклеить к нижней части 1.
Нет, вот этого ты не можешь.
Ну вот я спрашиваю. То есть, как бы, ну, если два конца были приклеены к одной дуге, то они должны оставаться приклеены к одной дуге, да?
Да.
Понял. Спасибо.
Ну, более конкретно, там симметрия квадрата просто. Можно отразить относительно горизонтальной оси, вертикальной оси, на 180 градусов повернуть. Вот 4 варианта.
Да, понятно. Да. Понятно.
Что? Нет, не вариант. Нет, хомфлип.
Ну, если он различает мутант, значит он не определен.
Окей.
Если у них графы одинаковые.
Okay, and let me state a theorem. Due to Sergei Chmutov and myself, which states that a Vassiliev invariant of order at most 10 cannot distinguish any pair of mutant knots if and only if the corresponding weight system depends only on the intersection graph of code diagram rather than the diagram itself. So that, okay, so mutant pairs are in fact very closely related to intersection graphs and weight system depending on intersection graphs only. If we have a weight system depending only on the intersection graphs of chord diagrams, then the corresponding knot invariant is unable to distinguish between mutant knots. And conversely, if a weight system does not depend does not depend. If there are two chord diagrams that can be having the same intersection graph such that the weight system distinguishes between these two chord diagrams, then there is then there are two mutant nodes, at least two mutant nodes, such that they can be distinguished by the corresponding node invariant. In particular, if we take these two nodes, the Conway node and the Kinoshita-Terasaki node, let me erase this parts. Then to each of these nodes, to each of these diagrams, we are able to associate a corresponding chord diagram. 11. They do have 11 intersection both. And the corresponding chord diagram can be constructed like that. Just consider each intersection point of the diagram as a chord. There are 11 elements. And we may number these double points in some way. 4, 5, 6, 7, 8, 9, 10, 11. And we can construct a chord diagram just by moving along the diagram. We meet point number 1, then point number 2, then point number, strangely, 11, then point number 3. No, let me, anyway. Point number 3, I continue that way. Point number 4, point number 5, point number 6, point number 7, then 8, then 4 once again, then 9, then 6, then 7, then 1. No, I must meet each point twice. Then 1, then 2, then 8, then 4. There should be 22 points. Sorry, let me, I do have not enough place on my circle to put all the points, but each number I meet twice when going along the diagram. And so I obtain a chord diagram, in this case with 22 chord ends, and therefore 11 chords. 11 chords, each chord corresponds to a double point of the diagram. And I will obtain a share in it. I will obtain a share like that. And the complementary share. And if I make a mutation inside this share, then I'll obtain the chord diagram corresponding to the plane diagram of the Kinoshita-Terasaki node. And these two chord diagrams will have the same, or better say, isomorphic intersection graphs. Well, and what do this statement mean? For example, if we are talking about colored Johns, this means that the universal SL2 weight system depends on the intersection graph of a chord diagram only. But this is not true for the universal SLN weight system. Which corresponds to the colored Humphrey-Petit polynomial. One of the problems I asked Joker to think about whether we are able to compute the universal SLN or universal GLN weight system for these two chord diagrams that can distinguish between the two. We know that the answer will be different. But even the efficient algorithms suggested by Kazaryan and elaborated by Joker does not allow one to compute the values for chord diagrams with 11 chords.
At the moment, only up to 7 chords.
Up to 7 chords, yeah. I believe that for weight chords, it also can work if we use some more sophisticated hardware. But to 7 chords, to 11 chords, this is still unreachable. And what we know, in fact, that each invariant, each Vasiliev invariant of order at most 10 does not distinguish mutants. Any pair of mutants. So order 11 is the very first order where we have some finite type invariants that can distinguish between mutants. Now, one of the questions closely related to this mutation is the question about which graphs are intersection graphs of chord diagrams. we have some graph and we ask ourselves whether this graph can be realized as the intersection graph of some chord diagram. It happens that the following construction due to called Cunningham decomposition helps to answer this question in a sense. What is Cunningham decomposition? What is Cunningham decomposition? Suppose we have a graph G, and its set of vertices V of G. And suppose that we have a partition, a disjoint partition of this set into two parts. Such that each part contains at least two vertices. This is U, this is V. And suppose that we have some subset of U and some subset of V, U prime and V prime respectively, such that each vertex in U prime is connected to each vertex in V prime. And there are no other vertices between U and V. Each vertex in V prime. And no other edges between U and V, W. It's not V, it's W, sorry. Then we say that we have a split of a graph. And a graph is said to be prime if it admits no splits. Is prime if it admits no splits. Then a theorem due to Cunningham says that first, any graph with any graph G such that it has at least 6 vertices admits a unique canonical split decomposition. Nope. Decomposition is said to be canonical a split decomposition is canonical if and only if each part is either prime or complete graph on n vertices or a star. A star is a graph, is a tree with a single central vertex connected to other. The problem with a complete graph is, let me add one more vertex. It has too many split decompositions. If you take an arbitrary set of vertices and a complementary set of vertices, then each vertex in one set is connected to each vertex in the other set. Нет, не надо. Here we do not have requirement that U prime does not coincide with U. No such requirement.
А почему тогда нельзя считать его, что это split decomposition на отдельные точки? И тогда в каком смысле юник? Вот я взял вот такой граф, он является canonical. Если я его разделю на, как это самое, на сплит 3 и 2, К3 и К2, то это тоже canonical, согласно этому определению.
Maybe I'm not too precise, but anyway, we do not split complete graphs. We do not split complete graphs. And the theorem states that due to Boucher, probably not, maybe Boucher, states that a graph is the intersection graph of some code diagram if and only if each prime graph in the Cunningham decomposition is an intersection graph. And moreover, A prime graph admits a unique realization as the intersection graph, if any. If any. For these two types of graphs, the complete graph and the star graph, it is obvious that each of them is the intersection graph and each of them is the intersection graph in a unique way. Да. And moreover, what we do have here, if we have a splitting of a chord diagram into a pair of shares, then for the intersection graph, this is exactly Cunningham decomposition. For example, in this case, we have the intersection graph, which looks like that for the rose share, and like that for the green share, and there are two vertices in the rose share such that each of these vertices is connected by an edge to a vertex in the opposite part, in the complementary share. Yeah? This is the rose share, and this is the yellow share. By obvious reasons, any two chords in different shares having ends on different arcs in the diagram intersect one another, while any chord in a share that has both ends on one and the same arc does not intersect any chord in the other share. So U prime consists of chords U prime and W prime are chords having ends on different arcs. So our theorem with Shmutov is based exactly on this Cunningham, on this split decomposition, because mutations of chord diagrams preserve intersection graphs, and Boucher's theorem guarantees that if two chord diagrams have the same intersection graphs, then one can be transformed into another by a sequence of mutations. Well,
А это конструктивные теоремы. По графу можно понять, он является примарным простым или нет? И если он простой, то можно понять, он является графом пересечения или нет?
First of all, there is an algorithm, maybe 10 years old or something like that, that constructs a split decomposition, the split decomposition of any graph in linear time. There is a linear algorithm with respect to the number of vertices which constructs a decomposition into prime graphs and complete graphs and stars. Now, for a given complete graph, for a given prime graph, there is an algorithm which is cubic in the number of vertices, which checks whether a given prime graph is the intersection graph of some code diagram, and one is able to make it cubic exactly due to this statement of Boucher that if a prime graph is the intersection graph, then its realization as the intersection graph is unique. So we know that there could not be many embeddings, many code diagrams providing a prime graph as the intersection graph. There is just one code diagram, or to be more precise, at most two, because if we take the reflection of a code diagram, then the intersection graph will be the same, but the code diagram, strictly speaking, will be different. So the uniqueness is up to reflection, is up to reversing the orientation of the boundary circle. Well, and of course, it is still the problem of distinguishing between mutants still does not have satisfactory solution, simply because computing this invariance for mutant nodes or even for mutant code diagrams is a complicated task. Maybe, I don't know, maybe there is a way to compute not the value of a weight system on a code diagram and on a mutant code diagram, but the difference of two values. Suppose we are not going to know, we take these two code diagrams corresponding to one plane diagram, the other plane diagram. We know that computing a weight system is difficult for each diagram, but probably we start with the difference of two code diagrams. Maybe there could be more efficient algorithms for computing these values for differences. But still, there is a lot of interesting thing. By the way, one of the I wanted to mention before, but I have not done this yet. One of the way to study nodes is to consider three-dimensional manifolds that are obtained as coverings of the node complement, ramified coverings of the three-dimensional sphere, ramified along the node. And it happens that if we consider these two nodes, or any pair of mutant nodes, and consider two-fold coverings of the three-dimensional sphere ramified along each of the nodes, then the covering spaces are homeomorphic for mutants. So this also is not a way to distinguish between mutant nodes. Okay, but you wanted to comment.
For SL2.
For SL2, yeah. Just, you're welcome. I think I am over, and let me give you
I cite one more theorem from the same paper of Chmutov and Lando, from the same paper, and it says that if you take SL2 weight system, or says that SL2 weight system and also GL11 weight system corresponding to Lie superalgebra GL11, they depend only, they preserve corresponding weight systems have equal values, take equal values on mutant core diagrams. And as a corollary, they depend only on the intersection graph. They actually depend on the intersection graph only. The second part is a corollary of the first one by this theorem. No, by which one?
Maybe you have erased it. Could it be?
Yeah, by this theorem. So the fact that the SL2, for instance, SL2 weight system is defined uniquely by the intersection graph, in order to prove that, we need to check that just for one mutation of a core diagram, the corresponding weight system is preserved. So I will, for a moment, I will discuss the case of SL2, just because we studied in details with Polida this case, and the proof is the following. So the proof for SL2. In fact, in a sense, this case is even slightly simpler because it's the corresponding weight system is what? Is a
Skew characteristic polynomial.
is a Well, it has a more reasonable explanations and straightforward computation, and it extends to the graphs. So for this one, the situation is slightly simpler. So
it is extended to graphs.
It's extended to graphs, not only to intersection graphs, but to graphs. For SL2 weight system, it's not known up to a moment. It's a conjecture by Sergei, long-standing conjecture that SL2 weight system could be extended to the graphs modular for term relations. Up to a moment, it's not proved yet. It's proved up to, it's checked up to graphs with at most 8 vertices by Zhenya Krasilnikov. Okay, so we compute for the mutant nodes. So we take for mutant chord diagrams. So we take a chord diagram, and we assume that our chord diagram splits as a join of two shares. And let's take one of these two shares, for instance, this one. And there is a Chmutov-Varchenko recurrence relation for the computation of SL2 weight system, and these Chmutov-Varchenko relations could be applied not to chord diagrams but to shares. If you apply this relation to a share, you represent this share as a linear combination of other shares. And if you take a join with the complementary share the same for all other shares, then the corresponding SL2 weight system will be the same. So we try to simplify. So our chord diagram is a join of two shares, and we try to simplify separately both shares entering to this join by applying Chmutov-Varchenko relations not to chord diagrams, but to shares. And applying these relations, this could be simplified. And as Paulina explained, this could be represented in her talk. This could be represented as a linear combination of shares of the form when we have several parallel lines, and the coefficients of these combinations, these coefficients.
Sorry, are you sure you are correct? What are the orientations of the arcs of the circle?
Well, this just the same.
And here is just the same, yeah?
Yeah. These coefficients polynomial in the variable C. So for the SL2 weight system, it takes values in polynomials in one variable C, which is a Casimir of the corresponding SL2 Lie algebra. A polynomial in one variable. So these are exactly the same C. So we represent.
Sir, Paulina comments that there should be two different C's. Yep.
No. at the moment, I would like to take just a single C. So we represent this share as such a linear combination. And now we observe that when we apply mutations, this share is mutant invariant. If you take any symmetry allowed by the mutation, this share is preserved. Either reflection or rotation preserves this share. And therefore, the value of the corresponding, just because of this symmetry, the value of the corresponding join will be the same. So this is the proof. The proof is over. However, I would like to make some further comment.
Just in case, if you replace such a share with the share where any two chord diagrams, any two chords intersect one another, whether the result remains true.
Sorry?
Вместо пучка параллельных хорд берем пучок хорд, которые все пересекаются друг с другом.
Да, тоже, да. Это другой базис. Другой базис.
This is just
So let me make one remark.
Сейчас, Максим, извини. Переход от, от таких, от набора параллельных ко всем перекрученным. Если просто верхнюю часть поменять ориентацию, то это не разрешенная операция?
Это не разрешенная мутация, нет.
Я не понимал. Ага, понял.
Это неразрешенная мутация, она, как видишь, она меняет граф пересечения у этих самых отдельных частей долей. Просто разрешается только вот так вот развернуть и вот так вот развернуть. Вот тремя способами.
Понятно. Спасибо.
Значит, remark is that such a decomposition is unique. So if you apply Chmutov-Varchin correlations in different order, you will arrive at the same, always at the same decomposition into this. This is first was proved by another Polina Zakorka. And actually, implicitly, if it was this statement was formulated in the same paper by Chmutov and Lando, and it's attributed to
Цукер.
О.
Нет, там LHTS. TS. TSU.
О.
Нет.
О. H.
TS. U. KI. Yeah. I.
So it's attributed to Tsuki, but the arguments are not, to my opinion, they are not correct. So after a small correction of these arguments, I will formulate another proof. So implicitly, this statement was known long ago, but was formulated not in a not sufficiently accurate way. So the idea of Atsuki is to take invariance, to introduce an invariant of shares taking with values in universal available algebra of SL2 tensor by itself. So the idea is just the same as the usual Kontsevich weight system associated with the Lie algebra. We put different indices and letters corresponding to different elements of Lie algebra, and then take corresponding words and take the sum. But in this case, since we have two different arcs, we have two different words. And therefore, we take the invariant, we have an invariant taken into the tensor product of two copies of universal available algebra. And then it was stated in that paper that the corresponding element belongs to the center of this product of these two algebras. And as we checked together with Polina, this is not actually true. The corrected statement is the following. So since we have two different, so the first details this definition need to be corrected in the following way. So the first thing is that when we take multiplication in this algebra, we should take the conjugate multiplication on one of the copies. So G1 tensor G2 times G3 tensor G4 is defined by as follows: G1 G2 tensor D3, but this in a different and opposite order, G4 G2. So probably I would take the dual one. And the second statement that we take not this one, but instead of taking the tensor product, we take the symmetric product. So we take by symmetry by the involution exchanging the components. So in this if you apply this symmetry, that the corresponding, this is again the algebra, and the center of this actually is a ring of polynomials in two variables, where C is C tensor 1, which is equal to 1 tensor C. Up to this involution, this is the same. And the X is the one corresponding to this share. So it's Casimir corresponding to the tensor product, the corresponding Casimir element. So without this symmetry, the corresponding weight system is well defined. So if you take values in this one, it's well defined, but it will not be a center. It will not be the center. The corresponding element will not be ad invariant. But after this symmetry, it becomes indeed ad invariant. And this element according to this product is equal to x to the power k, where k is the number of quartz. And so this invariant is nothing but this one. So it takes values and the ring of polynomials in two variables. So it has, each element has a unique representation as a linear combination of monomials in X as a coefficients of polynomial in C. So now it's over.
Okay, thanks. Are there any questions, comments? No, thanks.
Я не понимаю, фактор это алгебра будет, да? Все-таки умножение это с разных сторон. Там. Если ты умножишь G1 тензор единицы и единица тензор G1, это один и тот же элемент получается?
Да, должно быть так. Это, значит, на языке этих самых, на языке вот этих sharers у нас умножение устроено таким образом.
Это за два действия у тебя переставляет порядок в мономах или нет?
Каких
что делает за два действия?
Каких мономов? Каких мономов?
Ну, элементы USL2 и USL2 бар можно написать как какие-то мономы в образующих.
Нет,
ну, как
образующих тут нет никаких. Образующих нет.
Сейчас давай нарисую. Значит, вот если у нас есть, значит, что мы там пишем? Вот мы пишем, расставляем тут какие-то элементы из алгебры Ли, которые в соответствии там с нашими хордами как-то они расставлены. Тут стоит Е, там ИТ, Е, ИТ со звездочкой, ежитое со звездочкой. И вот, значит, мы такой доли сопоставляем такой элемент. ЕИТ, ежитое, тензор, ЕИТ со звездочкой, ежитое со звездочкой. Мы идем по направлению ориентации и перемножаем все мономы. И это то же самое, что мы сначала... У нас порядок этих самых двух не важен, поэтому это все равно, что ЕИТ со звездочкой, ежитое со звездочкой, тензор, ЕИТ, ежитое. Это как мы определяем соответствующую весовую систему. А умножать их нужно таким образом. Значит, если у нас есть какая-то доля здесь, if we have a share, one share and another one, и мы, as a result will be like that.
Да, понятно, да.
So if you have G1, G2, G3, G4, we multiply in the following way. G1, G3, G4, G2. So G1, G3, G4, G2. Yeah, like that. So we go multiply this one by that one, and then another copy is this one by that one.
Okay, let's stop here. We have still 3 minutes before the next seminar. 3-minute break. Thanks.